So I'm going to derive the situation now for an ideal case. Ideal case means Hooke's law must hold. There is no friction, and the spring itself has negligible mass compared to this one. Let's call it a massless spring. So now I'm going to write down Newton's second law, ma, which is all in the x direction, equals minus kx. A is the second derivative of position, for which I will write x double dot, mx double dot. One dot is the first derivative, that's the velocity. Two dots is the acceleration. Plus kx equals 0. I divide by m, and I get x double dot plus k over m times x equals 0. And this is arguably the most important equation in all of physics. It's a differential equation. Some of you may already have solved differential equations. The outcome of this, you will see, is very simple. X is, of course, changing in some way as a function of time. And when you have the correct solution for x as a function of time, and you substitute that back into that differential equation, that equation will have to be satisfied. What would a solution be to this differential equation? I'm going to make you see this oscillation first. I'm going to make you see x as a function, and I'm going to do that in the following way. I have here a spray paint can, which is suspended between two springs, and I can oscillate it vertically, which is your x direction, like that. So x changes with time. The time axis I will introduce by pulling on this string. When the spray paint is going to spray, I'm going to pull on that string, and if I can do that at a constant speed, then you get horizontally a time axis, and of course vertically you will get the position of x. So I want you to just see qualitatively what kind of a weird curve x as a function of time is, which then will have to satisfy that differential equation. All right, it's always a messy experiment because the paint is dripping, but I will try to get this spray paint going. There we go. Okay, now I'll pull. All right, could you give me a hand? Yeah, could you please? I will cut it here, and then you be very careful because it is messy. Or let it take it out this way. Okay, just walk back. Just walk, yeah, great. Yeah, hold up the top so that you can see it, fine. Okay. What does it remind you of? Sinusoids. It reminds me of a cosinusoid, by the way. Sinusoid or cosine, same thing. All right, well, let's try to substitute in that equation a sinusoid or a cosine solution. Whichever one you prefer, makes no difference. So I'm going to substitute in this equation, and this is my trial function, that x as a function of time is a constant a, I will get back to that in a minute, times cosine omega t plus phi. This a we call the amplitude. Notice the cosine function, the highest value is +1 and the lowest value is -1. So the amplitude indicates that is the farthest displacement from 0. On this side would be +a, and on this side would be -a. So that's in meters. This omega we call the angular frequency. Don't confuse it with angular velocity. We call it angular frequency, and the units are the same. The units are in radians per second, the same as angular velocity. If I advance this time little t, if I advance that by 2 pi divided by omega, if I advance this time by 2 pi divided by omega, then this angle here increases by 2 pi radians, which is 360 degrees, and so that's the time that it takes for the oscillation to repeat itself. So this is the period of the oscillation, and that is in seconds. And you can determine, if you want to, you can define the frequency of the oscillations, which is 1 over t, which we express always in terms of hertz. And then here we have what we call the phase angle. And I will return to that. That's in radians. And this trial function, I'm going to substitute now into this equation. So the first thing I have to do, I have to find what the second derivative is of x as a function of time. Well, that's my function. I have here first the first derivative, x dot. That becomes minus a omega. I get an omega out because there's a time here. And now I have to take the derivative of the function itself. So I get the sine of omega t plus phi. Of course, I could have started off here with a sine curve. I hope you realize that. I just picked the cosine one. X double dot. Now I get another omega out. So I get minus a omega squared. The derivative of the sine is the cosine. Cosine omega t plus phi. And that is also minus omega squared times x. Because notice I have a cosine omega t plus phi, which itself is x. So now I'm ready to substitute this result into that differential equation. This must always hold for any value of x, for any moment in time, and therefore the only way that this can work is if omega squared is k over m. So omega squared must be k over m. And therefore, we now have the solution to this problem. So we have omega equals the square root of k over m, and the period is 2 pi times the square root of m over k.